Hello, this is Sherry Kraber. I am a statistician at StatEase. We are based in Minneapolis, Minnesota, and I am very happy to have you here. Today's topic will be how many runs do I need using power and precision to size your design of experiments? I have my email address here. If you have questions that you want to ask after the session, I am happy to answer them. If you do have any design expert or StatEase 360 licensing questions, please send those to sales@statease.com. They will be happy to help you. So to make the most of this webinar, everybody is on mute. I will address questions afterwards, but you are welcome to type in your questions into the questions pane, and I will see them there. This presentation will be posted to the webinars page of our website, hopefully by tomorrow. And so I would encourage you to go to our website, click on Learn DOE, and then find the webinars page. The agenda that we're going to follow is looks like this. First of all, I'm going to talk about sizing designs or DOEs based on the objectives of your experiment. And then we'll get into using power to size factorial designs with a case study, and using precision to size response surface designs also with a case study. Actually, a couple case studies. So we typically talk about experimentation with a kind of a strategy that follows the SCORE method: screening, characterization, optimization, and verification, or sometimes we have other words for it. And a more complete discussion of this method can be found in our webinar called Know the Score for Multi-Factor Strategy of Experimentation. That is posted on that same web page that I just referred to, our webinars page of our website, or it's on our YouTube channel. So with screening, we are usually looking at a lot of factors that we aren't sure what their effect is, and trying to determine which ones have big effects that we would carry through to further studies. So the objective of this design, a screen design, is really to detect main effects, find those significant main effects, unbiased from any interactions that may exist. From there, we probably move on to a characterization design, and both of these are typically done using factorial designs. But now with characterization designs, we can detect and define the interactions that occur between factors, and we may even go ahead and check for curvature at this point. But in both of these, screening and characterization, really our objective is to detect some type of effect. If we want more information about our system, then we're going forward and looking into optimization designs, which are typically called response surface methods, and mixture designs would also fall into this category. And our objective here is to make precise predictions. So we are assuming that we've already found the effects of interest, but now we really want to get good models of that design space and really be able to make good predictions so that we can optimize well. So with factorial designs, the focus is on using screening and characterization designs to correctly identify main effects and interactions. And we ask the question, what are the important process factors? What are the important interactions? So for this purpose, the idea of power is a great statistical tool to help us evaluate how well the design is going to work for us, and especially to determine the appropriate number of runs. Now, when we move over to the response surface and mixture designs, our focus changes. Now we want to model a response surface to optimize and make predictions. And as I said, we should already know at this point which effects are the important ones. But we really want to know how well does the response surface represent the true behavior of our system. And so using the statistical tool of precision is a better measure to ensure that the experiment design is sized correctly. So we're going to look at both power and precision in this talk. So let's start with power for Factorial Designs. We can follow a good planning process. So this is our DOE planning process, in which we start by writing down our opportunity, the objective, what are you really trying to accomplish out of this particular experiment? Now, once you've written that down, and people overlook that step all the time, but it's really important that you actually have a written definition of what you're trying to do. After you do that, then we want to quantify your objective so that we can properly size the design. And so this consists of a few parts. Part A is defining the minimum change in the response that's important to detect. That's your signal. What's the smallest change in the response that's important to you? And I'm going to describe this a little bit more on the next slide. Okay. B is actually the easier one. Estimate the experimental error or the standard deviation for each response. What's the natural process variation of this response? If you have measured this response over some time, I'm quite sure that you can dig into some historical data and pull up information on the variation of this response over some period of time. You have to decide what is a reasonable set of data to use to estimate the standard deviation, but it should include normal variation that you would find in your process, day-to-day process variation. And then we put those two numbers together to form a signal-to-noise ratio, which we use to estimate power. Okay, so let's go back up to A and talk about defining that minimum change in a response. So to define your signal, you ask, what's the minimum amount of change that would be recognized as an important improvement? This answer is a business decision. It's not a statistical calculation. It's really thinking about, how much effort and work do you want to put in to detect, a certain amount of change in the response. Let's look at an example. Let's say you want to improve yield from its current level of 80%. Okay, if you asked a manager, what amount of improvement in yield would be important, he'd say, well, any amount of improvement would be great. I'd love to see if you can improve yield at all. That would be great. But that's not precise enough, because I'm sure that he doesn't want to spend, hundreds of thousands of dollars on experiments to improve yield by, 0.5%. That's probably not going to be financially feasible. So we have to quantify what really is the minimum amount of improvement that's of value to the company. So let's put a little finance hat onto this. Let's say each percent is worth $100,000 per year in profits. Well, then what amount of improvement is valued. You know, if you could get a 10% improvement in yield, well, that would be $1 million. I'm sure anybody would go for that. You know, that would be exciting. What about a 1% change in yield? Then, you know, you could increase your profits by $100,000. Probably still important to the company. And how about a 0.1%? You know, that's maybe getting down where maybe there's bigger fish to fry. Maybe there's other things that could do that could increase your profits more rapidly. So, you know, maybe or maybe not, it's a business decision. What is the minimum change in yield that would be valued by your company? So discuss this with a team and decide on what your number is. That would be the smallest number that the design is going to declare is statistically significant. Then you go ahead and choose your variables that you want to study and the ranges. Now remember that when you are choosing your factor ranges, you have to choose low and high levels that are far enough apart that they are likely to change the response by at least that minimum change that you're looking for. So this might take a little bit of range finding studies to figure this out, but you know, this is something that you really want to think about, is setting those factor ranges. Again, that's not something a statistician can tell you. It's subject matter knowledge. So finally, based on all of that information, you can start choosing your design and look at things like aliasing and power. And of course, make sure that all your factor combinations are safe and are going to give you some meaningful information. Okay, so another way of representing this change is by looking at it graphically. When we're talking about the smallest change in the response, we are talking about what happens when the factor is changed from its low level to its high level. What is the change in the response? You know, how much does it increase or possibly decrease? You know, so it's really the slope of this line. Okay. If we were to look at an 8-run design with trying to detect a signal of 2, a change in the response of 2, given that the standard deviation of that response was 1, so this gives us a 2-to-1 signal to noise ratio, that little 8-run design would have a power of 57%. So the software would show 57% for this 3-factor design. And what that is telling you is that if you run this 8-run design and you have a factor that changes the response by 2 times more than the noise, your ability to find that, identify that factor, will be just over 50%. So maybe you will, maybe you won't. That's not a very good scenario to set yourself up for success. You know, we would prefer, when we're setting up a designed experiment, that our likelihood of success is much higher than that. Probably, as it says down here, power should be approximately 80% or greater for the effects that you want to detect. So taking that 8-run design and replicating it, doing 16 runs instead, then gives actually a power of about 95%. So this is much, much better. This means that your likelihood of finding this change in the response is now, you know, 19 times out of 20, 95%, really good. That is certainly the power that you want. So going back to some definitions, again, what is power? How does it compare to other things? Well, let's look at this truth table. You have some population of data. That population of data contains the truth. Either there are effects, yes, or there are no effects, no. Now, when we run our designed experiment, we take a sampling from that big population, and we run the ANOVA on this sample. And the ANOVA is either going to say, let's say it says to reject the null hypothesis. There is something statistically significant. If that is the truth of the population, then that's great. That's exactly what we're looking to find. If the ANOVA says, hey, there's something significant here, and perhaps the p-value is like around 0.05, and the population truth is that no, that effect is not significant, then that is what's called a type 1 error, or your alpha risk, and that's a false alarm. That can happen fairly easily. You know, we definitely get false alarms, especially with those p-values that are lower, like the 0.05, even 0.02, 0.03s can definitely still be false alarms. So this is the alpha risk. The opposite of an alpha risk is your confidence. So when we say that, let's say we get an alpha value of 0.01, then we might say that we have 99% confidence that that's a significant effect. It's not an exact statement, but you know, it's similar. Okay, how about the other side of things? Let's say that the ANOVA says to retain the null hypothesis. That means there's no effects. If that's the truth, then that's good. Again, we've made a correct decision. This would be great if you are trying to do a validation design or a verification study where you're trying to prove that maybe your final process is stable and does not have any variation to it, and you're looking to demonstrate that there are no effects in your system. So that's great. But what if the ANOVA says there are no effects, and the truth is there are effects there? Then that's a type 2 error, a beta risk, and it's a failure to detect effects. Okay. The opposite of that is power. This is where power comes into play. Power is that 1 minus beta. It's the probability of finding an effect of a certain size relative to the noise as measured by the signal to noise ratio. We want power to be high, at least 80%, for the effect size that we're interested in. Okay, so let's demonstrate this with a case study. So we are going to look at a mouse cell fluorescent assay done in a 96 well plate. So we have 96 wells. That means we have the opportunity to potentially do up to 96 runs. Our objective is to maximize the signal from the assay. We decide that we want to detect a change of 400 fluorescent units. That's the response. So this 400 fluorescent unit change, that's the minimum change that would get us interested and demonstrate that, hey, we found an effect. Now, unfortunately, historical data is telling us that the standard deviation is also around 400. That means that our signal to noise ratio is about 1, 400 to 400, about 1. When it comes to calculating the power of the design, it's the ratio that's the important thing, not the numbers themselves. So if you don't know the exact numbers, you can just put in, a 1-to-1 ratio or a 2-to-1 ratio or something that you think is representative of the system. The default of Design Expert is a 2-to-1 signal-to-noise ratio, as we found that's a pretty reasonable estimate. Okay, so we have factors like the number of cells and the amount of stimulant and the amount of substrate concentration. This is simply a 2 to the 3rd design. So let me open this up. Okay, so this is the Design Expert part of our new product, STADIS 360. And this is a 3-factor 8-run design. We'll click Next. We have our factor names in here. Next. And we are going to put in, we have our response. We want 400 signal and a 400 noise. That gives us a signal-to-noise ratio of 1. Then the next screen will tell us for a signal-to-noise ratio of 1, the power to detect this is only about 20%. That means that if 5 of you were to run this same 8-run design on the same system, of the 5 of you, 4 of you would not find any effects, but 1 of you would. So remember that this number is the probability of success. It's the likelihood of finding it. It's not telling you you're not going to find it. It's just telling you that the likelihood of finding it is pretty low. 1 in 5 will. So, we don't want to run designs with such a low probability of success. So we want to increase the sample size. Now, there's not, just a quick sample size calculator, because the sample size itself depends on the exact design that you choose. So every design is calculated uniquely. So what we have to do is simply click on the back button. We're going to back up here and go to our beginning screen and increase the number of replicates. So rather than just do 8 runs, we replicate, now we have 16 runs. And we can go forward and check the power. And now we're at 45%. So we've more than doubled power. So we're making progress. It's not as good as we would like yet. We can go back. I'm going to kind of jump ahead. I'm going to go up to 4 replicates. Oh, now we're at 77.9%. Now we're getting somewhere. The recommendation power should be approximately 80% or greater. I usually say somewhere in the 75 to 80% range is good. Note that these numbers are going to be red as long as you are below 80%. As soon as they go above, then they'll turn black. But I have a 96 well plate here. My runs are actually pretty cheap. I can definitely do another replicate. So I'm going to go back and do 5 replicates. And then I get to that magic number above 80%. So now my likelihood of detecting effects should be quite high. All right, so that is 40 runs, 8 runs times 5 replicates, 40 runs. I could finish and build that design and then collect all of my data. And should have success with this. Okay, so as we were building and adding runs, power keeps increasing. If we wanted to add, a 6th replicate, we could certainly get higher power. It provides diminishing returns as you go up and up, but if you have the budget to do more runs, certainly there's no harm in doing that. It's just doing a little bit more work. So power, again, is the probability of finding an effect. It depends on the size of the change in the response. So the larger the change in the response, the higher the power. It depends on the size of the standard deviation of the response. If you have a smaller standard deviation, the power is going to increase. So anything you can do within your experimental system to keep the noise down will be a benefit to power. Larger designs have more power. And of course, if the design itself isn't larger, then you can add replicates. And the more runs, the higher the power. Okay, so that's a look at power to detect effects. Now let's shift our emphasis here to looking at precision to size response surface designs, which includes mixture designs. So I have an example of each. Now, with response surface designs, there's a variety of designs you can use. There's a webinar, Keys to Building Response Surface Designs, that I would refer you to if you want more information on these. But there's a central composite design, box Bankin design, and optimal design. All of these have slightly different design spaces. You can see with optimal design, you might even have constraints on the design space. And the goal is to model the design space well to obtain precise predictions. So, there's a big change in what our goal and objective is. We're no longer just trying to detect effects. Power is the ability to detect an effect. Precision is how well you're going to make predictions. The precision of your predictions is going to depend on a couple of things. It depends on the location in the design space. So let me just back up. Our design space is contained by all of these combinations. Here's a picture of a design space. So precision depends on where in the design space. Are you in the middle, or are you at one of the corners? Where in the design space are you? Okay, if we look at just one factor, a one-factor experiment, our design space is essentially from the low level of factor A all the way to the high level of factor A. And if you see this dotted black line, that's your confidence interval. And that confidence interval is narrower in the middle and wider towards the edges. That confidence interval is calculated from both the location in the design space and the standard deviation of the response. So you need to know both of those things. Now, in this case, we have, we would often state that we would want our response to be estimated plus or minus some amount of precision. So, maybe your response is yield and you want to estimate it within plus or minus 2%. So that plus or minus 2%, we just assume is constant. That's the red line. It's constant across the entire area because we're saying this ahead of time. We're not defining our area yet, but you can see that where that red line, or I should say where the confidence interval is within the red line, then we're getting predictions that are precise enough. And so, really from this green line to that green line, that's the area that we're getting precise predictions. And then outside this, the confidence interval is actually going wider. It's bigger than what we want. And, so we really want these green lines to span more like 80% of the design space and not just the middle 50%. And so we have a tool called the fraction of design space that's really going to help calculate how much area of the design space is going to give us precise enough predictions. So you have to start with answering the question, how well do you want to make predictions of your response? The more precision you want, the more data is required. So you might make a statement like this. We want to estimate the mean response, the average response, with a precision, that's your D, of plus or minus 0.8. And then you also have to estimate the standard deviation, just like power. It's the same number as you would use for power, typically estimated from historical data or prior experimentation or other means. The larger the standard deviation, the more data is required. And so, you might say historical data provides a standard deviation of 0.5. Here's a few other examples. Viscosity, you might want to estimate viscosity plus or minus 0.15. And then your standard deviation is this. So just a few different types of responses. You have to define the precision. You have to calculate the standard deviation. Okay, there are two tools that are used to estimate precision. The first one would be the standard error plot. So the standard deviation of the response that you provide is turned into a standard error of predictions. It's just a conversion. And this particular example is a two-factor face-centered central composite. And the graph is the standard error of the design, standard error of your predictions. And so you can see that the innermost ring is 0.45, and then it goes up to 0.5, 0.6, 0.7. And in 3 dimensions, it would look like this. So you can see that the middle, the center, has the least amount of error. That means you're going to get the best predictions in the middle. And the predictions increase in their error as you go to the edges and especially to the corners of the design space. This is actually a big reason why we do replicates of the center when we're doing response surface designs, because the replicates in the center of the design space pull down this graph so that you get your best estimates in the center region, which is presumably where the optimum is. You've probably taken a guess as to where you think the optimum is, and you probably centered your design around it. So it's natural to assume that you'd want the best predictions in the middle region of the design space. Now, this graph can be found under evaluation, graphs, contour, and as a matter of fact, I can pull one up here. I'll just take this one, for instance. I'm going to go to evaluation, graphs, and contour, and I would get the standard error of that particular design. And here's a 3D surface of it. So, of course, lower is better, but there's no particular spot at which it's deemed to be bad, just lower is better. Now, This is easy to look at when you just have two factors. You know, it's certainly easy to look at. What if you have 3, 4, 5, 6 factors? Then you would have to look at the standard error graph in all those different dimensions. So you would have to look at AB, AC, AD, BC, BD, and all those different dimensions. That just becomes cumbersome. So rather than having to look at the standard error in all those different dimensions, what we're going to do is we're going to take this new graph called the fraction of design space, and we're going to use that to accumulate and tell us how much of the design space is covered, can estimate to 0.45, how much can estimate to 0.5, to 0.6, 0.7. Okay, so here's your standard error graph. And this changed a little bit to 0.43, but this is the related FDS graph, where this 0.43 includes about 25% of the design space. So this center squarish shape represents 25% of the design space. If we go out to the 0.5, that contains about 50%. If we go out to the 0.61, that contains about 75% of the design space. So the fraction of design space graph provides a profile of the prediction error across the design space. And we're going to want to search for a design or size a design so that about 80% or more of the design space gives us predictions that are precise enough. Okay, so let's look at a case study. And this particular case study you can go to Design Expert, the help system, tutorials, and find the response surface tutorial. That's the data that I'm using. So we have 2 responses here, 3 process factors. It was a 20-run central composite design. We are trying to maximize the conversion. That first response, we're trying to get a targeted activity level, 63. Then our DOE process is just like a factorial design, except that we are going to now define the precision needed. So we want to estimate our conversion to plus or minus 5%. That's the precision we're looking for. And we are estimating activity to within plus or minus 1.3. Then standard deviations for each response are shown here, 4 and 1.1. Now we have to form our signal to noise ratios for both responses. So here's the conversion signal to noise ratio, 1.25, and the activity signal to noise ratio of 1.18. Now, since this is the worst case scenario, this is the one that we are going to evaluate with the FDS graph. Okay, so let me pull this up. And you would do this before before getting any data. Oops. Just trying to clear this out. Okay, so you would build your design. So power is built in upfront. Power is always present as you're building the design. Precision is found under design evaluation. So you actually do have to build your response surface design first, and then go to evaluation, which is over on the left here. And then you can just jump right over to graphs. We're evaluating a quadratic model. And here's our FDS graph. It comes up by default. And then we need to put into the FDS tool our worst case delta, which was 1.3, and sigma, which is 1.1. After that information is put in, then there's a crosshairs put on here, and it converts this sigma of 1.1 into the equivalent standard error of a mean. So there's just a little math behind the scenes that's done. And then we figure out, well, how much of the design space can fit to that precision. And it turns out that the FDS, the fraction of design space, is 0.84, or 84% of the design space, or can fit to that precision or better. Okay, that's great. That means that this 20-run design is sufficient. We can go ahead and be confident that the majority of the design space is going to work, 84% of it. We can look at the 3D of the contour plot. You know, it's nice and flat. And certainly the areas that are going to have higher standard error are going to be the areas right at the corners. Yeah. So as long as your optimum ends up being in the middle, you're going to be good. If your optimum does end up being at a corner, then just the precision of that optimum will not be as high, as good as if it was in the middle. It doesn't mean we can't predict it. It just means that the confidence interval has gotten larger, and you know, it's just a little bit less precise. And of course, that was the worst case response. Conversion, which was a higher signal to noise ratio, will be better. So the rule of thumb for precise predictions is that you want your FDS graph to be greater than 80%. That's also the goal for power. And you can improve FDS again by increasing that precision that you're looking for, decreasing the noise, or increasing the number of runs. With optimal designs, increasing the number of runs is very easy. Can be done by rebuilding the design and adding additional model points. So that's what I'm going to demonstrate next with a mixture case study. So in this mixture case, we have we're creating a flare with 4 chemicals, and each of the chemicals is constrained to some region with a total of 1 or 100%. We're trying to find the blend that gives a maximum illumination, and we're going to use a special cubic model for this. So we're going to build this design and check to see if it has adequate precision. Okay, so just I'm just going to go through that build process with you. Reuse, yes. All right, so this is a mixture optimal design, 4 components, total of 1. Here's your ranges for each of the components. And in the optimal page, we made sure to change the model to a special cubic. It has 14 required model points, 5 lack of fit, 5 replicates, for a total of 24 runs. Okay, so then we have to build this. And then we have to go to design evaluation and graphs. It will calculate the FDS graph. All right, so we have the graph built now. I have to go back to my slides and check. We want to estimate D, the illumination with a precision of plus or minus 6 and standard deviation of 4.5. So we need to put in 6 and 4.5. And we find out that the FDS, the fraction of design space, is only 0.54, and it's red. So that's indicating that a little bit more than 50% of the design space would predict well. Of course, that's going to be in the middle, but that's not good enough. Usually you'd want it to be more like 80% or higher. So we're going to have to get more runs. How do we get more runs? Well, we're going to rebuild this and add some additional runs. So we're going to say yes to reusing the same info and just kind of loop around. And we're going to add additional model points. If you want to estimate your model better, then putting in more model points makes the most sense. And this would be a little bit of trial and error. How many more model points do I need? You often don't need a lot more. In fact, I'm just going to add 4 more. It's not a lot more work. And then build that design. And go to evaluation again. Go to graphs. This is a whole new design, so you do have to retype your numbers. 6, 4.5, and now the 28 run design now gives us an FDS of 0.87, or 87% of the design space predicts with this amount of precision. So that is good. Now I would feel confident in running this design and knowing that when I find my optimum and I want to make predictions around that optimum, that I would be doing it with enough precision. Okay, so this slide says, assuming that there are already 5 each for lack of fit and replicates, then increase the number of additional model points. So, the defaults of the design are the required model points plus 5 replicates plus 5 lack of fit points. So make sure that those haven't been compromised, that you haven't changed them. And if you have changed them, then you should first bump those up, but then add some additional model points. All right, so I know that many people have been using power and already, and they tend to overuse power and go ahead and try to use power for analyzing response surface designs. Power is not the right metric. Power is your ability to detect effects, which is perfect for factorial designs. But it is not the interest of response surface designs. For response surface designs, the question is really, how well does the surface represent true behavior? So if you want to size a response surface design, then precision is the appropriate statistic to do that. You need to make the switch from power to precision. And again, precision is found under design evaluation. So size your DOE appropriately for its type and purpose. Factorial design, size via power. RSM and mixture designs, size for precision. Focus on the ability to predict the mean response to a defined amount of precision. For power, you define that delta Y is the minimum difference you want the DOE to detect, or the minimum change in the response that you want the DOE to detect. You also need the standard deviation of the response. and then size to achieve a power of 80% or greater. For fraction of design space on the RSM and mixture, define the precision of the predicted mean. And again, the same standard deviation, excluding factor effects, and size to achieve the FDS of 80% or greater. All right, so that is a summary of both power and prediction and using them so that you can answer the question, how many runs do we really need? If you want some references, I've included some references here. As I noted, this entire presentation and the recording will be available on our website shortly. Now, we cover all of this power and prediction information in our DOE workshops. And so these are the two workshops that we hold publicly, the Modern DOE for Process Optimization and the Mixture Design for Optimal Formulations. So if you want to learn more, I would encourage you to look into attending either of these. They are primarily available via distance learning, so you can access them. We are also, if the times that we allow aren't good for you, there are some asynchronous options as well. If you just contact workshops@staties.com, we can see how we can accommodate you. Other resources are the trio of books, the DOE Simplified, RSM Simplified, and Formulation Simplified books. Those are available in soft cover, and they're also available online as ebooks. You can contact the publisher's website to get more information, or Amazon also carries them. So with that, I will conclude this presentation, and I can stick around for a few minutes to see if anybody has any questions. But I would like to thank you for attending, and check back with us in January for a whole new set of educational webinars. Thank you very much.